Hello everyone. Have you ever wondered how much energy does a single photon carry? A photon may be unimaginably small, yet it packs a definite punch of energy. That energy is given by the equation E equals h times nu, where E is the energy of one photon in joules, h is Planck's constant, 6.63 times 10 raised to the power minus 34 joule-second, and nu is the frequency of light in hertz. Since frequency nu equals c divided by lambda, we can also say E equals h times c divided by lambda, that is, energy equals Planck's constant h times speed of light c divided by wavelength lambda. Even a small laser beam releases billions of such photons every second. Let's calculate how. Let's calculate the energy of a photon emitted by a laser. We are told that the laser emits monochromatic light with a frequency of nu equals 6.0 times 10 to the power 14 Hz. We also know Planck's constant, h equals 6.63 times 10 to the power minus 34 joule-second. The formula for photon energy is E equals h times nu. Now let's substitute the values. E equals 6.63 times 10 to the power minus 34 multiplied by 6.0 times 10 to the power 14. Carrying out the multiplication, we get E equals 3.98 times 10 to the power minus 19 joules. So, each photon emitted by this laser carries approximately 4 times 10 to the power minus 19 joules of energy. Now let's find how many photons the laser emits each second. The laser power is given as P equals 2.0 times 10 to the power minus 3 watt. Each photon has energy E equals 3.98 times 10 to the power minus 19 joule. The number of photons per second is given by n equals p divided by E. Substituting values, n equals open bracket 2.0 times 10 to the power minus 3 close bracket divided by open bracket 3.98 times 10 to the power minus 19 close bracket. Calculating gives n equals 5.0 times 10 to the power 15 photons per second. So this modest 2 mW laser emits nearly 5 quadrillion photons every second. Next, let's take Caesium, a metal with a low work function. Given Phi naught equals 2.14 electron volt. To find the threshold frequency, we use Phi naught equals h times nu naught. Therefore, nu naught equals Phi naught divided by h. First, convert the work function to joules. Phi naught equals 2.14 multiplied by 1.602 times 10 to the power minus 19, which equals 3.42 times 10 to the power minus 19 joule. Now divide by Planck's constant, nu naught equals 3.42 times 10 to the power minus 19 divided by 6.63 times 10 to the power minus 34. That gives nu naught equals 5.16 times 10 to the power 14 Hz. This means any light below that frequency, say yellow or red, will not cause photoemission from Caesium. Now, suppose photoelectrons are stopped by a potential of 0.60 volt. We can find the wavelength of the incident light using Einstein's equation. Start with EV naught equals h nu minus Phi naught. Rearranging gives nu equals open bracket EV naught plus Phi naught close bracket divided by h. Since nu equals c divided by lambda, we can write lambda equals h times c divided by open bracket EV naught plus Phi naught close bracket. Now let's substitute. H equals 6.63 times 10 to the power minus 34. C equals 3 times 10 to the power 8 meter per second. V naught equals 0.60 volt, Phi naught equals 2.14 electron volt, and 1 electron volt equals 1.602 times 10 to the power minus 19 joule. So lambda equals open bracket 6.63 times 10 to the power minus 34 multiplied by 3 times 10 to the power 8 close bracket divided by open bracket 0.60 plus 2.14 close bracket times 1.602 times 10 to the power minus 19 close bracket. When you compute that, you get lambda equals 4.54 times 10 to the power minus 7 meter, or 454 nanometer, which lies in the blue region of visible light. Let's now connect power, intensity, and the quantum nature of light. First, remember that the power of a light beam depends on the total number of photons emitted per second, not on the energy of each individual photon. So, when we increase the intensity of light, we are simply increasing the photon count, not the energy carried by each photon. The energy per photon depends only on the frequency of the light. This is given by the formula E equals h nu. Higher frequency means higher photon energy and lower frequency means lower photon energy. And this leads to an important conclusion: even a dim beam of ultraviolet light, which has high frequency, can eject electrons easily, while even a very bright red light, which is low in frequency, cannot eject a single electron. Because in the quantum world, frequency controls energy, not brightness. Let's end with a quick summary of how we analyze light using photons. First, each photon carries a fixed amount of energy given by E equals h nu, or equivalently, E equals hc divided by lambda. So a photon's energy depends only on its frequency or its wavelength. Second, the number of photons emitted per second is found using N equals power divided by energy per photon. So brighter light simply means more photons are arriving every second. Third, the work function of a metal decides the threshold frequency and the threshold wavelength needed to eject electrons. And finally, Einstein's photoelectric equation ties everything together: the energy of light, the frequency of photons, and the emission of electrons all connect through one simple relationship. This is the quantum view of light, a world where energy comes in packets, and every photon counts.